Okay, so let's get started here. So we left off last time, we were on section 2.2. We're looking at different displays of data. In this case, we are looking at basically what we call a quantitative data. The data all involves numbers itself. So the first thing we're going to look at, this kind of way of doing it. So we've already dealt with a frequency distribution before. We looked at that last time, but now we're going to have to think about it a little bit differently because now our data is actually going to be numbers. And so what you can imagine is you can imagine the data, it says age of people in a certain state who have a high school diploma. So we'll pick a state, looks like it's a little bit of a smaller state. And then we'll say, okay, everyone who's between age 17 and 23 has a high school diploma. And so we will record the ages of those people. So we can see that 212,000 fall between 17 and 23. 199,000 fall between 24 and 30, and so on as we go down the list. A few things we're going to define: the lower class limit. Each of these different rows basically is a class. This is the class of people 17 to 23. This is the class of people 24 to 30, and so on. So within a class, you're going to have a lower and upper class limit. And it's pretty darn simple. It's just the lower limit is the first number, the upper limit's the second number. So in class 3, the third class, the lower limit is 31, the upper limit is 37, and so on. It's pretty straightforward. Now the class width, the size of each class, if you will, how large it is, how many different numbers it encompasses, is kind of what you can think of as the class width. It's not the upper limit minus the lower limit of a given class. It's not quite like that. It's actually the lower limit of succeeding classes and the difference between them. So the class width of this data is going to be 24 minus 17. 24 minus 17. And so it's actually going to be 7 in this case. The class width is going to be 7. We'll actually answer that question there in just a moment. So let's do this so we can see most of everything. Age of people in a certain state who have a high school diploma. Which age group did the most people fall into? Well, we go over here. This is the frequencies here, and it's this one, the third class, because 235,000, that's the most, and that's the age group of 31 to 37. So I'll write that, the 31 to 37 group. Which age group did the least people fall into? Should be able to read that right off, pretty straightforward. It's 38 to 34. How many people were studied? We need to add, I'll do that with text. We'd need to add 212 plus 199 plus 235 plus 168. And I'll be a little lazy and just use a calculator. It's not lazy, but you understand how to add, so you can save yourself a little time. Calculators are only appropriate when you know the theory behind something. You know you could do it, but you need to do it quickly. So the answer would be 814. And since the data is in thousands, it's really 814,000 people. How many people are 31 or older? Well, only these last two classes give that. It'd be 235 plus 168. Pretty straightforward. And that's going to give you 403. So 403,000 people are 31 and older. What's interesting is if it tried to ask how many people are age 27 and older using this data, you don't have enough information because 27 does not fall cleanly on the edge or is on a lower class limit. So that wouldn't quite work because you don't know exactly how many of the people in this group, the 24 to 30-year-olds, are 27 and up. So you can't quite do that with the data as presented here. The class width, we argued, you take succeeding classes, so we'll just use the first two, and you take the difference in the lower class limits. So 24 minus 17, and that's going to equal 7. So the class width is 7. You just as easily could have said, oh, well, I could use the second and third one, 24 and 31, and that still works out to 7. What was the lower class limit for the group that had 235 people in it? Oh, here's the group with 235, really 235,000 people in it. The lower class limit is 31 from that group. What is the upper class limit for the group that had 212 people in it? 212,000. It's this group. The upper limit's 23, the number 23, Jim Carrey's worst movie. What percentage of the people are 24 to 30? Now we need to make a little bit of we need to do a little calculation here. We know there are 814,000 people in total. What percentage of the people are 24 to 30? So we take the number, the frequency 199, divide it by the full 814, convert that to a percent by multiplying by 100, and we'll round to 2 decimal points. You see almost 25%, about 24.45% are that way. And then a histogram, we don't exactly need to do that per se because it's very straightforward. I'll kind of get it going for you. Oops. Well, we're not going to have enough room, but just imagine your histogram would be like this, X's and Y's. Along the horizontal axis here, you would put the actual classes. So the 17 to 23, you can almost just call it the first class, or you can write 17 to 23, then 24 to 30, and then you're just going to draw your bars above that. You can use all the same color. This one is that one, that one. Remember the histogram, in the histogram, the bars touch. So, that's not exactly what it looks like, but that's what it would be. Along the y-axis, you'd have numbers. You could go from 0 to maybe 250 on top and count by 50s along the y-axis. So pretty straightforward. Again, none of this should be new or surprising. We're just kind of reviewing it almost is a good way to think about it. One last note I'll make about this is, say you were just given a bunch of data. Say you were just given, here's a bunch of data, and it's all the ages. It's 17, 23, 23, 35, 37, 42, 41, 38, 25, 25, 26, 31. You're just given a bunch of data like that, and you had to create your own frequency distribution for it and make a histogram out of that. The one note I will make that should be useful to you is that in general, the class width it's going to be your largest number, whatever your largest value in the data set is, minus the smallest value in the data set. And you're going to divide by the number of classes you want. How many classes do you want? Do you want there to be about 8 classes? Up here in that data before, there's only 4 classes. You usually want anywhere from 5 to 15 classes, but that's not a hard and fast rule. You do this calculation, your largest value minus your smallest value, whatever the difference is, you divide it by the number of classes desired, and then you round up to the next value that makes sense. The next value that makes sense. So if all your data is in whole numbers, you might want to round up to the nearest whole number. And always round up, not down, or your width isn't going to be large enough. Stem and leaf plots are pretty interesting. They're not the most interesting thing on planet Earth, but they're just another way of displaying data. What you have is you have your stems and you have your leaves, and you will have a legend down here that tells you exactly what's going on. So when you see 4 and then on the other side of the bar is a 5, that represents the number 45. What you can then do, you can make your stem and leaf plot. In this particular data, the stems will be the tens digits, the leaves will be the ones digits, but that doesn't always have to be the case. If all your data was like 9.3, 7.2, in that case, you'd make the stems the 1 digits, and the leaves, you'd make them the tenths digit, the first value after the decimal point. So it just depends on what you have. And it's very straightforward, especially once you see what I'm about to do with it. So let's say for 4, what we're really looking for is data in the 40s. So let's see, we've got 47, so I'm going to put a 7. Then I'm going to give a little space, go find the next value in the 40s, and it looks like there isn't one. There's no more data in the 40s. So that's the only thing. So this is saying there's only one data value in the 40s, and it's 47, 47. In the 50s, which is not the decade I was born in, 57, so I'll put a 57. Put a little space, next 50s, 54. Put a little space, another 57. And if you have repeats, you make sure to put them in as repeats in the stem and leaf plot. But it looks like there's nothing else from the 50s. In the 60s, and you want the leaves to start as about so that they're all lined up like over here, because you'll see the purpose of the stem and leaf chart in just a moment and why you need that. So next we want values in the 60s. We got 66. We've got 67. And it looks like there's no other values in the 60s. Let me double check through that. Nope. The 70s, it might get a little bit interesting. So let's see, 76, we got that. 73, 74, 71. Whoops, let me put some spacing. There we go. And it looks like those are all the values in the 70s. In the 80s, which is the decade I was born, the very tail end of it. Literally, I was 6 months left to go in the 80s. So in the 80s, we've got 82. We've got 80, so we'd put a 0 here. 88, 82. Excuse me. 82, 84, 81, and another that's just 80 itself. And then finally in the 90s, oh, let's see, 94, I see, 99, and a 91. So this would be our stem and leaf plot. Looks pretty good for me doing it kind of freehand with a text box. So look at this. What this tells you is that there wasn't a lot of data in the 40s because look at the leaves. They don't jut out that far for the 40s. You had a little more in the 50s, not as much in the 60s, a little more in the 70s. Definitely in the 80s, we had the bulk of our data in the 80s, and then our 90s, not a whole lot. You can almost think about this as like a histogram on its side, and you could kind of do that. Imagine flipping that histogram onto its side, and that's exactly what it's really kind of showing you. It's telling you how much the data clumps around certain values. And it looks like the 80s, it clumps around the most. What we're going to see is this is going to have a certain type of skewness that we're about to address here in just a moment. And so that's interesting. A few other quick notes about the stem and leaf plot. Make sure, like I tried to right here, wasn't 100% perfect. Make sure your leaves all kind of line up, because if they don't, you're not going to see this effect necessarily. Make sure you put equal spacing everywhere. So I use just 2 spaces on my space bar for each of the numbers. But if they had all been spaced weirdly, the 80s might not have looked as large as they really were. So you just have to be careful so that you can see this effect forming here of where the largest values go. A dot plot. A dot plot is going to be interesting. It's almost like another type of histogram, but it's not quite a histogram. What we're going to do, a dot plot is going to count up frequencies of things. So let me show you how the dot plot works. And again, it is not horribly complicated. We're going to create a horizontal axis. Along the horizontal axis, we're going to put each of the possible values up there. So it looks like the values range from as low as 10 up to 18. Yeah. So along that axis, we're going to do 10, 11, and I'll fix this. we can put them along the horizontal axis. And then for as many times as that specific value shows up, we're going to put a dot above it. So I'll use this. That may not look good, so I can just freehand a dot. That's fine. Or a stamp. How about a stamp? No, they don't have a good color for it. Okay, or a good shape, I should say. So the number 10, let's find all the occurrences of it. It looks like 10 only shows up once. So I'm going to put a single dot above 10. It's almost hard to see. So that's 10. 11. There's actually no 11s, it looks like, in this data. So we completely skip it. 12. 1, 2, 3 12s. So I'm going to put 3 dots above it. I'm going to try again to make sure they're equally spaced so I can see the effect that I'm going for. It's like a pseudo histogram almost. 13s, I got 1, 2, 3, 4 13s. So I'm going to put 4 dots above it. Very straightforward. Four dots, you know, and it's not going to be perfect, especially if you're doing it by hand. But when you're looking at a computerized dot plot, one you'll likely see in your homework, it's pretty straightforward. It's very straightforward. You can see the dots will be perfectly placed. 14, looks like we're going to have a lot of 14s. 1, 2, 3, 4, 5, 6, 7. 7 14s, so 2, 3, 4, 5, 6, 7. It's good enough for government work, as they say. 15, we got 1, 2, 3, 4, 5 15s. So 1, 2, 3, 4, 5. 16s, we've got 1, 2 16s. 17, we've got 1, only a single 17. 18, we've got just the 1. So again, the dot plot, I call it a pseudo histogram because you can kind of see this shape forming. It goes up a little, comes down, and that's awfully big. Let me just get over it. Something like that. Oh, comes down a little bit, down, and then that's kind of like a shape that's forming. It looks like most of the data is clumped around the middle. Now that's nice. That's not always going to happen though. In fact, the shape that data takes is really interesting to us because if you look at a histogram, there's going to be 4 principal shapes we're going to look at. First of all, the uniform shape. Uniform means that basically all the bars are about the same height, all the way from left to right. They are uniform. Uniform means always the same across the spectrum. So this is going to be your uniform shape here. And I'll even write it. Maybe I don't need to circle it. That looks bad. Just uniform. Bell-shaped is exactly what it sounds like. Bell-shaped, it almost looks like a bell that goes ooh like that, and this is clearly going to be it. C here. Move that around just a little bit. So bell-shaped. Again, you imagine drawing over it. It's soft on the edges. On the edges, it's not very high. Then it clumps up in the middle, and then it comes back down on the other side. That's going to be what we say is bell-shaped. Now, a right skew, this is actually going to be skewed right here is what we're going to call it, and I'll explain why. So look at the skew right shape. It starts off small, comes up real quick and clumps around here, and then it slowly goes on to the right after that. This is actually a really interesting shape that's formed. So skewed right looks something like that. Maybe I'll make it a little bit less symmetric looking because it's strictly not symmetric. It looks something like that. That's the skew right shape. How do I know something skewed right? Imagine you took the standard bell curve. this nice bell shape, we call it. It's roughly symmetric, short of my ability to draw it. It is roughly symmetric. You could put a line down the middle and it would just be like a mirror image. What I've done for a skewed right shape is I've taken the bell curve and I've grabbed it. I say, you give me. And I grab this side of it and I pull it to the right. And that's what's doing here. The bell curve is being pulled to the right, so it's skewed right. What that means is that there's not a lot of values that are large that are on the right side over here, but they are so large that they still have some kind of impact. They still pull the curve to the right. So even though there's not a lot of them, the fact that the values are that large has an effect on the graph like that. So that's what it means to be skewed right. And then skewed left is just going to be kind of the opposite. Imagine I took the standard bell curve, let's say that was drawn well, and I come over here on the left side of it and I pull it to the left. I pull it to the left. So it looks almost something like this. That's going to be a skewed left shape. It's like someone pulled it to the left. And so, squared, skewed left. It's going to be the leftmost one there. So those are going to be basically the 4 different shapes that we're going to be interested in studying. We will revisit this. We will especially be revisiting the idea of being bell-shaped. The bell-shaped curve is the histogram, if you will, of something called the normal distribution. And we use the normal distribution all the time in statistics. We are going to be using it heavily in the back half of this course, in the second half of this course. So remember that bell shape, bell shape, bell shape. It is so brutally important. We can talk about the skewness, but we can't do a whole lot with them, frankly, in this statistics course because they require a different level of analysis. But the bell shape, we're going to go into super detail about that. So keep that in mind. Finally, a time series plot. I'm not super interested in going over it. It's so simple, it's not even worth mentioning. Imagine an XY plot. So just a standard graph. And along the x-axis, time is going up. Time is slipping into the future. So you'd have January, February, March, April, May, June, July, August, etc. And then you would just literally connect the dots with a line graph. It would be like, it went up a little. Oh, it went way up. Went down a little. Oh, it went way down. Oh, yes. Good morning, Vietnam. There. That's all a time series plot is. It's very, very, very straightforward. It is not going to give anyone any grief. Okay, so that is nice and dandy like apple candy. That's a little saying that you might hear people say. What people? I don't know. Me. I'm a people. I'm a people, aren't I? I think so. So that's going to be it for section 2.2. 2.3 is going to be the last section of chapter 2 that we're going to look at carefully. So let's check it out. Cut it out. All right. So section 2.3 is concerned with misrepresentation of data. It is concerned with bad, ugly ways that you can demonstrate data. And some of it is just clearly whoever is showing off the data is just lying. Sometimes it's just that they're lying. But usually it's just mistakes, or it's people taking artistic liberties with some of their charts and graphs that ultimately obscure the point that is trying to be made, or make it very hard to just read what the heck's going on. So here's some general tips for when is data bad, and making sure that you don't incorporate it in your own chart, and how to find charts and how to look at charts and say, oh, that's awful. So title, label. Oh my goodness, labels are so important on charts. Now, when I've been doing it, I've kind of been skipping that a little bit or just kind of showing you the numbers. But what you really need to do is you need to include labels for what you're doing so that people can look at it and say, oh, okay, I know exactly what you're talking about. This is clearly a pie chart. Here's what it's measuring. Or this is a bar graph. Here's what it's measuring. If you need to include any units of measurement, have at it. Avoid distortion. What does distortion mean? Making the data look like something it's not. And there's a lot of ways you can do that. So don't lie about the data. If you're using a bar graph, make sure the bars are proportional. If you have one data point that's 10 times larger than another, the bar should be 10 times larger than the other bar. If it's only twice as large, you made a mistake. It's not going to look right. So the bars should be proportional. White space on the graph is kind of difficult to look at. It makes the graph like kind of ugly, to be honest. Don't put so much clutter on the graphs that, you know, you're just like, what is going on? I can't read this thing. There's too much information and too much crap on it, to be honest. Oh, 3 dimensions. 3 dimensions is horrible. 3 dimensions is trash. Do not use 3-dimensional graphs. Ooh, look, the pie chart has been rotated on its side and it's 3-dimensional. Don't do that. Resist the urge to do 3 dimensions. Never do 3. I mean, that was like 1990s Microsoft Word crap that nobody does anymore, and it always looked bad. So let's get away from that. Don't try to fancy it up, make it all artistic at the sacrifice of making the data readable and clear. If you like, ooh, I want it to look like some Claude Monet painting, and I'm like, okay, that sounds like a cool idea for a chart, but if you have to make it all weird and abstract and it's not, the data's not clear, you've defeated the purpose of it. Unfortunately, I hate to say this, I love art. Don't get me wrong, I love art. I love art in many forms. I go to museums. All that business. I love it, but this is math. This is statistics. We're here to talk about logical things, not quite artistic things. So you cannot sacrifice clarity for art. Avoid relative graphs that are devoid of data or scales. I agree with that sentiment. Look at these two charts here. Look at these. These are time value charts, or data over time. It's what we kind of skipped there at the end of the last section just a few minutes ago. Look at this. Oh my gosh, look at life expectancy. The life expectancy in 1950, oh my gosh, it's almost at the bottom. Look what it is here in 2000. That's like 15, 20 times higher. It's way up there. Oh my goodness. People are living to be 15 times as old as they were just 50 years ago. No. Look at this. Look at the y-axis. The y-axis didn't start at 0. It didn't start at 0, and that's a problem, because it's what that does is that horribly messes up your scale. That messes up the scale of your data and how far apart the points are from each other. This is like interval data. Remember, we talked about the 4 levels of measurement: nominal, ordinal, interval, and ratio. Interval data did not have a 0 that meant anything. So in this case, it's kind of like that scenario. Without you having a 0 and putting it on the chart, this is misleading. It doesn't look right. But this is the proper form of that same chart over here on the right. We started our thing at 0, and okay, it's not as dramatic. It's clearly gone up over the years thanks to better medical technology, capitalism. but but it's not as dramatic as it was before, because that's truly not how it is. So this one blows your mind. This one's like, okay, that makes more logical sense. And it's all because we started with a 0 that allows us to use a proper scale. So this looks kind of like how ratio data is. And then finally, we can look at these pie charts. It says which chart is misleading. I would argue they're both misleading, because for this one, I mean, it's 3D. And I just said, I was vehement when I said 3D is bad. 3D is ugly. 3D, no to 3D. It makes the pieces that are at the front look more visible than the ones in back, but that's arbitrary. That doesn't matter. Who cares if it happened to be down here or up here? They're still equally important to be analyzed and seen. But either way, even on this one that's not 3D, I would rather just use whole solid colors. You try to use these weird patterns, and maybe you can tell what's going on, but you want to be as clear as possible. And sometimes you can look at these and say, whoa, what is that? What is it? And imagine you were printing this off in black and white. Of course, you'd have that same problem if you had different colored slices, but still, I don't like using patterns in my pies. I'd rather use different colors, and make sure they're not lurid. Make sure it's not like bright red and right next to it is like puke green or something like that. Make sure the colors are differentiable from each other, but still kind of smooth and flowing. You can use a little bit of artistic flair on that when you're dealing with pie charts and the like. One homework, and I say homework loosely, one little homework assignment, there's a BuzzFeed article. Um, there's a BuzzFeed article that deals with actual um, things that that particular writer found in real news articles, newspaper articles. What's a newspaper? I don't even know what a newspaper is, but apparently it's news that has been printed out on physical paper. But no, this writer scoured the internet, scoured all kinds of sources, and she found a bunch of charts that were just very poorly represented. Some of them look slick. They're like, ooh, that looks like futuristic slickness. But it actually, if you really look closely, the article discusses why those are really bad. So that article is called 13 Graphs That Are Clearly Lying. Look for it on BuzzFeed. You can literally go into the Google, almighty Google, and just type this exact thing in. And you should be able to find it. It's by Katie Notopoulos. And you can see some examples, and yeah, you're going to be shocked. There's some legit sources in here. There's the Florida Department of Law Enforcement put out a graph, and the graph is really bad. It's a bad chart because they made the y-axis upside down. There's other places that you can find. There's baseball. There's like about the pitcher R.A. Dickey and his knuckleball velocity. And they're just bad charts that shouldn't be used. And these are like legit sources by people who are supposed to know better. So go check that out. That should really kind of help you understand this section a little better. It's a little bit of a fun section. And that's going to do it for chapter 2. And I hope you guys all have a wonderful day.